Well, hello there. This is the video on transcendental derivatives. So we're going to talk all about what are called transcendental functions, meaning the functions that go beyond algebra, like beyond addition and subtraction and multiplication, division. An example of a transcendental function is something like our exponential function or our logarithmic function or our trig function. And the question, of course, is, well, how do we take the derivatives of these types of functions? Well, here we go. Let's find out. In this video, we're going to have a different sorts of examples here. Some of them involve actually trying to prove some of our transcendental derivatives. I'm going to go on to the next slide in just a second, but basically the idea is that we're going to have to kind of accept a few of them on faith for right now, and then when we go to the next video, we'll be able to actually prove all of these down the road. But I wanted to introduce them to you first. So the derivatives for our trig functions are as follows. Like I just said, we need to have the quotient rule to prove the last four, but we're going to get acquainted with them for now. One of them is that the derivative of a sine of x is cosine of x. Hopefully we've done a little exploring of that up until now and realize that there's an amazing connection between the sine function and the cosine function, and that's that the derivative of sine is cosine. We also have the derivative of a cosine is negative sine, all right? And these properties will allow us to discover many wonderful things about the cycles of how sine and cosine derivatives go back and forth. You'll notice that there's got to be some sort of a pattern there, that the derivative of one is the other function, all right, maybe with a negative attached. A couple of other derivatives we need to know are derivative of tangent of x, which is secant squared of x, and the derivative of secant of x, which is secant of x tangent of x. So like I said just a minute ago, we're going to have the quotient rule to prove these two, right? But for now, as you're getting ready to kind of memorize them and know them, know that each pairing has two secants and one tangent. So what do I mean by that? Well, the derivative of tangent has the two secants, while the derivative of secant has the other secant and a tangent. So they're the same sort of patterns that we see throughout here. And as we'll talk about in class, derivative of cotangent is not that hard to remember if you remember the co part of this. All right, and what do I mean? So derivative of tangent is secant of x times secant of x. Derivative of cotangent is negative cosecant of x, cosecant of x. So notice I just put a co in front of everything. And then as we'll learn, the derivative of all the co-functions is negative. All right, so derivative of cotangent altogether is negative cosecant squared of x. Derivative of cosecant of x is negative cosecant of x, cotangent of x. So notice how I emphasize that. Cosecant versus secant. Notice that they're the same derivatives except we put a co in front of everything. So the derivative of secant of x is secant of x tangent of x. Derivative of cosecant of x is negative cosecant of x, cotangent of x. So all the co-derivatives have a co in front of, or they have a negative in front of them, excuse me. And then there's a relationship between the derivative of tangent and cotangent and secant and cosecant. So for example, let's figure out how we actually got the derivative of sine of x. So we'll have to go back to our original definition, and that is dy dx equals the limit as h goes to 0 of sine of x plus h minus sine of x all over h. So this is the limit of a difference quotient here. Now, one thing you might remember from way back in pre-calculus is our addition formulas for a sine function. So sine of x plus h can be rewritten as sine of x times cosine of h plus cosine of x times sine of h, and then minus this extra sine of x here. All of this will be then put over h. So you'll notice that I was able to expand sine of x plus h basically by just a rule that we have in pre-calculus, all right, into sine of x cosine of h plus cosine of x sine of h. If you rework this a little bit by writing this as the limit as h goes to 0 of cosine of x times sine of h over h plus the limit as h goes to 0 of sine of x cosine of h minus sine of x all over h, all right, we'll notice that we get some pretty nice derivatives, pretty nice limits right here. So if you remember, that limit is important. Limit as h goes to 0 sine of h over h. And then when we factor this second part, we'll see another limit that's important, and that's the limit as h goes to 0 of cosine of h minus 1 over h. So if you remember way back when we were learning the squeeze theorem, we learned that this limit right here, limit as h goes to 0 of sine of h over h, is 1. And then this limit right here, limit as h goes to 0 of cosine of h minus 1 over h is equal to 0. Right, so those are limits from a previous unit. And then when we bring back the cosine of x and the sine of x, which have nothing to do with h, right, they're just, we can pull them out because they have nothing to do with the limit themselves, we just end up with cosine of x. It's a pretty amazing proof, actually, and pre-calculus certainly plays a role in it. Okay, for exponentials, we've got another set of derivatives that we need to know. All right, exponential derivatives are amazing, and we'll talk a little bit more about them in class. But one of the more famous derivatives we're going to learn about is that the derivative of e to the x is just e to the x itself. It's the only function that we've got that is its own rate of change. It's pretty remarkable, and we'll talk about it a little bit more in class. Related to that is the derivative of any exponential, a to the x, as long as a is a number that's bigger than 0 and not 1. So we've got derivative of a to the x, which is a to the x times natural log of a. And as it turns out, these two rules actually relate to each other very much, because if we use a base e, this formula here on the left becomes e to the x times natural log of e, and natural log of e is just equal to 1. So it reduces down to e to the x. So basically what I'm getting at is this is the one major formula right here, and the formula on the right is a specialized version of that. We also finally have our derivatives of our logarithms. So the derivative of log base a of the absolute value of x is 1 over x times natural log of a. And then we've got a very special derivative right here, which is the derivative of natural log of x, which is 1 over x. So let's start with a little bit of a proof here of the derivative of e to the x. And how do we go about finding that derivative? Well, as always, we want to make sure that we start with our limit as h goes to 0 of e to the x plus h minus e to the x all over h. So this is using our difference quotient. One of the things maybe that you'll notice is that we can rewrite e to the x plus h as e to the x times e to the h, all that minus e to the x over h. And then you'll notice that I've got an e to the x in my numerator that I can factor out. So I end up with limit as h goes to 0 of e to the x times e to the h minus 1 all over h. All right. Now, we're not going to do a formal proof right here, but we want to investigate what this limit as h goes to 0 of the e to the h minus 1 over h is. You can see here with this nice little table of values, it looks like that value of the limit is approaching 1, and you can also verify that with the graph of e to the h minus 1 over h. All right, so that limit's equal to 1, so our whole derivative is equal to e to the x. Pretty fascinating. I mean, we got some interesting derivatives that are going to play huge roles later on. All right, write the derivative of a to the x, y equals a to the x, and y equals tangent of x, also as limits of difference quotients. So we won't go through and solve these, but let me show you how you would go about doing this. Right, go back to your difference quotient, and we would say the derivative of a to the x is limit as h goes to 0 of a to the x plus h minus a to the x all over h. All I'm asking you to do there. If I wanted to do the same for tangent, that would be the limit as h goes to 0 of tangent of x plus h minus tangent of x all over h. Right, so this is going back to our days when we first started learning about the derivative. All right, so how do we find the derivative of y equals natural log of x? Right, we said just a minute ago that derivative is 1 over x. Well, where's that coming from? So we have to take a trip back into pre-calculus and notice that y equals natural log of x means that x equals e to the y. And why is that? Well, natural log and e to the x are inverses of each other. So I switch my inputs and my outputs, and now I get x is equal to e to the y. So now I'm going to pull a little bit of a trick here that you're going to see later on when we do our implicit derivatives. And I'm going to take the derivative of x with respect to y. Whoa, you can't do that, can you? Yeah, absolutely. Right? I just got to watch what I'm respecting. So x is my dependent variable and y is my independent variable. So that means that dx dy is equal to e to the y. We just proved the derivative of e to the something is e to the something. And so what does that mean? Well, dx dy is the reciprocal of dy dx. So dy dx equals 1 over e to the y. And what do we know what e to the y is equal to? Well, e to the y is equal to x. So dy dx is equal to 1 over x. I'm just fascinated. There's so many interesting derivatives here. It's kind of like you were going through, you're doing the power rule, and it seems so logical. And then now all of a sudden, derivative of natural log is 1 over x. Where's that coming from? All right. And it all has to come from our idea of what an inverse is. All right, last thing on this video here, if the derivative of a function is also differentiable, the second derivative, which is denoted by f double prime, is the derivative of f prime. So you may have seen this chart before, but just as a little recap, all right, remember we've got our f prime notation, our Lagrange notation, all right, which indicates which derivative we're on. The fourth derivative, for example, is the derivative of the derivative of the derivative of the derivative, right? And then we can go on and talk about the nth derivative. And if we're using our Leibniz notation, we put that d2y, we put the 2 right in there in between the d and the y, and then after the x. So this is the second derivative right here, third derivative, fourth derivative. And when we talk about second derivative, of course, we're talking about the derivative of the derivative. Third derivative is the derivative of the derivative of the derivative. Well, why am I bringing this back up again? Well, because I'm going to ask you to find crazy things like the 71st derivative of f of x equals cosine of x. How am I supposed to know that? I don't know. Well, let's see. If we keep on taking the derivative of cosine of x, all right, we're going to cycle back and forth. So I just showed you on an earlier slide the derivative of cosine is negative sine, which would make the second derivative the derivative of negative sine, which is negative cosine of x. The third derivative, all right, is the derivative of negative cosine of x, which would be positive sine of x. So notice how I'm rotating back. And then the fourth derivative would be cosine of x. Notice it takes 4 cycles to go back and forth between cosine, negative cosine, and sine, and then back to cosine. So all you got to do when you have to find one of these big derivatives up here, like the 71st derivative, is to figure out where we are in the cycle. We divide our number, our 71st derivative, in this case what we call our order, by 4, and then find the remainder. Well, 71 divided by 4 gives us a remainder of 3, so that means we're at the same spot as the third derivative, which would be sine of x. So these problems look intimidating, but there are lots of patterns. I could easily ask you what's the 71st derivative of e to the x, right? And then if you were paying attention, you recognize the derivative of e to the x is always e to the x, right? So you're always going to get e to the x, no matter which derivative I ask you to find. All right, in summary, there's so many derivatives. I know. It'll take a while. You need to get some flashcards. All right, I'll give you some tricks in class to help you remember them. And pre-calculus was helpful in trying to prove some of these derivatives we found. And these transcendental derivatives often come in cycles, so be on the lookout for repetition in our higher order derivatives. It'll be key going forward. Thanks for listening, and we'll see you on the next video.